Hey folks, this is Major Jones here to talk to you about machine code and assembly code. And we have four objectives today, which are to describe the two types of instructions that are available to us in the hack machine language. These are the two instructions that we can ask the computer to do for us. And we can represent that in two different ways, in the machine, what's called the machine code or the assembly code. So the second objective today is to show you those representations, make sure you can differentiate between them and convert back and forth between the two. And then hopefully at that point, I'll have shown you enough of the assembly code and you can kind of see what capabilities this computer has so that you can start using the assembly code to write small programs, 5 to 15 lines of assembly code that do simple tasks. So let's get started. Okay, so recall that this is recall from the last lesson that this is the model of the computer that we're going to use. This is our hack computer, right? And so what this means is that I have my ALU, which we looked at 2 lessons ago, that can do addition, subtraction, increment, decrement, those sorts of things. We have my ALU that can perform those operations on the D register, always on one side, and either a value in the A register or a value coming out of memory, which is at the address specified in the A register. And that the result of my ALU operation can go back to one of those three, or really we'll see any of those 3 locations, either the A register itself, the D register, or back to a spot in memory, again specified by the address in the A register. And that all of this is controlled by the control unit, right? The control unit sort of turns on and off all the registers and sets the operation code to the ALU, and it gets its instructions from the program memory. Our program counter starts at 0 and increments each clock cycle. So my program starts at memory address 0, and the instructions that I want this computer to perform are loaded beginning at address 0 and going sequentially kind of down to higher spots in memory. So you can see here on the left-hand side, I have a representation of that program memory. It starts at address 0 and increments downward. And inside that program memory, I have, a couple of series of zeros and ones that specify a instruction, a thing for my computer to do. And so believe it or not, these ones and zeros actually have meaning. We'll look at that right now. So the hack CPU can understand 2 types of instructions, an A type and a C type. The A type is super simple. So if what comes out of the program memory is a string of 1s and 0s, for which the most significant bit is a 0, then what we're telling the hack CPU is that we want it to load a value into the A register. And the value is whatever comes after that first 0 as an unsigned number. And so this is how I can sort of load literal values into my A register. The C-type register is the other type of register. The C-type instruction is the other type of instruction. And if there is a 1 in the most significant bit here, you can see that that indicates a C-type instruction. By convention, the 2 bits that come after that are also 1s, although those don't necessarily have any meaning. And in the C-type instruction, then I have 4 fields, 4 values that specify what I want my computer to do. So I have the not A/M field, the field for the opcode, what I want my ALU to perform, and then I have fields, 3-bit fields for the destination and the jump. Okay, so let's start with these last 2 because I feel like those are new, but they're easy to understand. So the destination field is 3 bits in C-type instruction that specify where I want my ALU result to be stored. And so you can see in the table here, they're labeled as D0, D1, D2, but honestly, they could as well be named A, D, and M because it's a 1 in any of those positions that will store the ALU result into either the A register, the D register, or the spot in memory whose address has the A register. And I can specify any combination of those. So you can see here at the very last row of this table, if I want, I can take my ALU result and store it in the A register and the D register and in memory. And so I can store it in any combination of those with this 3-bit field. The 3 least significant bits of the C-type instruction are what are known as my jump bits. Okay, and so you can see here, J2, J1, J0 specify if I'm going to change the flow of control in my program. A jump means to sort of jump to a different spot in my program memory, to not simply go to the next instruction. And this is super powerful, right? we'll see in the next lesson how I can use this to implement conditionals and for loops and while loops and all kinds of cool stuff. So you can see in this table, J2, J1, J0 correspond with which inequality I'm checking. I can specify no branch, no jump to be performed. I can do test if a value is greater than, less than, equal to 0, or any combination of those. And I can also set these bits to all 1 to indicate that I want to jump unconditionally, regardless of whether or not the ALU result, the output here, is equal to anything. So you can see that the two ALU flags that came out, right, the bits that indicated whether the result was 0 or negative are sufficient to tell us whether the ALU result is 0, positive, or negative. And we can compare those values with our jump bits up here to determine if we jump at all. So if, for instance, the 0 bit is set and the negative is 0, well, then that clearly indicates that our ALU result is 0. And if the ALU result is 0, then there are actually 4 lines in here, if I'm not mistaken, 4 lines in this table that correspond to taking a jump. So I would jump if the ALU result was 0 and my J bits were 0, 1, 0, right? Because that's in a line where the output equals 0 is true. I would jump if the J bits were 0, 1, 1, because this just checks if my ALU result is greater than or equal to 0, and it's equal to 0, so that's also true. I would jump again if the J bits were 1, 1, 0, because here I'm checking if the output is less than or equal to 0, and one of those is true. And I would also jump, of course, if the J bits were 1, 1, 1, because it doesn't matter what the ALU result is in that case. I would just take a jump, right? So I can affect a jump anywhere in my code based on the result of the ALU and whether or not that value is greater than, less than, or equal to 0. Now, an important note about this is that there's a bit of an implied task, which is that when I jump, my program counter will get the value that's in the A register. So that's just sort of part of this little architecture here. I didn't quite draw it, but there's a little line maybe coming from the A register going to the program counter to indicate that that's the value that gets sort of loaded into the program counter if I effect a jump. And so for this jump to make sense, right, prior to me telling the hack computer to evaluate the ALU result and take a jump, is to make sure that the A register has the correct address in my program memory where I want my instructions to kind of go next, my instruction execution to go next. Okay. The opcodes here, these 6 bits directly correspond to the little opcodes that we sent to the ALU 2 lessons ago. So they are ZX, NX, ZY, NY, F, and NO. Hopefully that's not a surprise to you. The last field in my CTAP instruction that I care about is this 1-bit field, which is not A/M. And it's this bit here that controls this multiplexer, that controls whether or not the other input to my ALU is coming directly from the A register or from a spot in memory whose address is held by the A register. And I think I've got it pulled up. If we look at the reading, you can see this table here that shows you how that affects the ALU operation. If that bit in my CTAP instruction is 0, then I'm selecting the actual value in the A register to go to my ALU. And so all of my operations are sort of performed on either the D register or some literal value in A. When that bit in my CTAP instruction is true, is 1, then the other side of my ALU comes from memory. So I've got a capital M here to indicate the data value in memory whose address is held by the A register. And so then you can see here that I'm performing effectively the same, I am performing the same ALU operations. It's just I'm performing those operations on now the D register and a spot in memory potentially, instead of the D register and the A register itself. With those 2 instructions, right, I can control basically every operation in my hack CPU, and I can start to use them to do useful things. All right. Believe it or not, these 1s and 0s here in blue are in fact legitimate hack computer instructions. But even if you're someone who worked with the hack code for a long time, looking at zeros and ones is not an easy way to read code. So this is technically called machine code because it is the format that the actual hack machine needs in order for that control unit to sort of direct the CPU correctly. But it's not super useful. Very early on in the development of computers and computer programming, folks realized that, hey, this is not going to work. We need something a little more advanced. And the advancement came in the form of assembly code. Assembly code is a technically human readable form of the instructions that we're going to send to our computer. I realize that this stuff in purple doesn't exactly look human readable, but it's at least more human readable than the stuff in blue. And it has the relationship where there's a more or less a one-to-one mapping between assembly code instructions and machine code instructions. So that the software programs that are able to convert assembly code into machine code are not super complex. So these, if you convert these zeros and ones using the formats of the A type and C type into instructions, they look like this, which means that my code first sets the D register to 0. Next, it loads the A register with the value 2. So the @ symbol here is shorthand for loading the A register with some unsigned value. Here on line 2 now, I'm performing the operation where D is incremented. So 1 is added to it and then stored back into the D register. And then on line 3, my ALU results is nothing. Doesn't matter because I'm performing an unconditional jump. Remember that I unconditionally jumped to the location in the A register. So the A register was most recently set back here on line 1 with the value 2. So that means my program counter gets the new value 2 after this jump is executed. And the next line of code to execute is back here, right? The program counter kind of jumps back to this line, number 2. Once the program counter is at this line, I again increment the D register. I go to line 3. I execute another jump. So this code here is a very simple 4-line piece of code that will continuously and infinitely increment the D register. Right? And you can already kind of see the format for the assembly instructions that are in my hack computer. So I still only have, right, this is still a representation of these two A-type and C-type instructions. It's just we're going to use sort of a more or less human readable format. So like you saw here on line 1, the @ symbol followed by a number is assembly instruction to load the A register with a value. Now that value can be a maximum of 15 bits and it has to be an unsigned or positive value, right? So that number has to be sort of in this range of 0 to 32,767. Second, I can perform some type of computation or C-type instruction. Now you see here kind of a 2 and 3 because even though this is, I have one instruction, I'm using that to do two things which are often best separated out. So one thing I can do is perform some type of ALU operation, and you can see the format for that is to list on the left-hand side of my equal sign the places where I want that value stored, A, D, and or M. In this case, in my example code, I'm just setting the D register, so that's the only one I have listed, but I can list more than one. And those are equal to one of the ALU operations that are available to us via the hack ALU. So I can increment D like I show here. I can set D to 0 because 0 is one ALU operation. I can perform, like an ANDing or something like that. And even though the jump is part of that C-type instruction, it's best practice to kind of separate that out. So I've got here listed in number 3, kind of the third type of assembly instruction you'll see is some type of jump. Now, if it's an unconditional jump, it doesn't matter what the ALU result is. So just like in the example here, I can just make this sort of a 0, something that doesn't affect the state of the processor, and execute a jump. The other kind of format you'll see for this is the ALU result is just the D register. And then based on the value in the D register, whether or not that's jump if greater than, jump if less than, then I can execute my jump. And so prior to these instructions executing, then it's commonplace to perform an ALU operation that sets the D register to test that value, and then to load the A register with the address in my program memory where I'm going to jump if this jump is taken. The reason why these two are separate, you can kind of see down here on the second line, is because it's easy to confuse the usage of the A register. At this point, we have one register, the A register, that can do any of three things, which is hold a numeric value that I want to use in an ALU operation. It can hold the address in data memory of a value that I want to do some operation on. Or if I'm going to use it to execute a jump, it would hold the address in program memory of where I want my program to sort of start executing next. And it's really easy to kind of to mix those up in a way that does not result in correct code. I won't say that they're impossible or you'll never see them, but it's typically a sign that something's not quite right when we're treating the A register as if it had both data and or data or program memory addresses. So even though this line of code down here is accurate, it's pretty unlikely that the A register in this case would hold both a data value that I wanted to add to D and also the address that I wanted to jump to if the result of that was greater than 0. Similarly, this line up here is kind of a red flag because it's unlikely that the memory location that I want to store the result of my ALU operation happens to be the same integer value that I want to add to the D register and store at that location. So these two lines of code are kind of red flags, and that's why you see up here that typically I'll sort of separate my ALU operations from kind of my jump operations. I won't say it's strictly that way. I think there's actually an ICE where it makes sense to actually break this rule. But that's typically the way you'll see it. Now if you, in class, what we'll do is we'll actually pull up an emulator. What am I looking for? That will actually help us sort of write and test these programs. So I'll show you how to pull this up in class, but I've got a program here that sort of has on the left-hand side my program memory. In the middle here is my data memory, and you can see kind of below those and a little to the right the important parts of the CPU, which are the value of the program counter and what the ALU is doing. And so here I can enter my code, right? So that my simple code to sort of do an infinite loop was D equals 0, address 2, D equals D plus 1, and then 0, jump. All right. And so this is the same assembly code that was on the notes here. If I hit the single step button, I'll execute one instruction at a time. So after the first instruction, D is equal to 0. It was initially, but if it wasn't, it goes to 0. Now I'm going to set the A register to 2. So you can see down here it got set to 2. And also the next line of code that's about to execute is being highlighted. Now I'm incrementing my D register, so that goes to 1. And then next, I jump back to line 2. So now my program execution goes back to line 2. I increment the D register. It goes from 1 to 2, and I jump again. And so this program, you can see here kind of in the D register just has the effect of incrementing D over and over again. All right. So as you are hopefully now capable of conceptualizing how you might compose little small programs to do like multiplication or something like that, you can also pull up the emulator here and enter your assembly code and kind of watch it run and make sure that it works. This is the same code that was running. Let's see what's in here. In this simulator, so I built a simulator which is broken now because I was editing it earlier. But if it's fixed before class, you can also in Logisim sort of enter that code and watch it run in a simulation of the hack computer. Okay, so that is these are the A-type, the two types of instructions that are in the hack computer, my A-type and my C-type. We looked at how we represent those in machine code, which again are the zeros and ones that actually get stored in memory to control the processor. And we also talked about how we might represent these instructions in assembly code, which is a more human readable format of that code. That's all I got, folks. I'll see you next time.